Hi everyone. Hopefully you all can see or hear me, or maybe both even. Everybody's very quiet, so. Hello. Okay. Just making sure that everything is still working fine. So, hope you're all doing good. Today we're going to be picking up from the two videos. We're going to review the building traversals, since that's the hard one. The traversals are easy. We can do an example of those too, but those are particularly easy to do. Building the tree is a little bit harder. It's easy once you get it though. It's really straightforward, but the first few times it's a little bit weird. So yeah. So before I start, are there any specific questions on the two videos that you all saw? Other than, I am going to go over building a traversal, but in general, questions about anything? I'll wait a minute to see if anybody writes any questions. I did have about 1 or 2 emails with questions, so I did answer those, I think. Where's my booklet, by the way? Oh, it's over there. Oh, I'll grab it. So, when I was gone last week, I did take a digital forensics boot camp that was supposed to be in person, but it went remote. So that was pretty fun stuff. If anybody's curious, what we did was they sent me a packet with some hard drives and some tools, a Tableau forensic duplicator, and this write blocker. And what you do is you plug in the evidence drive. So you raid, FBI open up and rate somebody, and then take their computers. They take the hard drive and then they copy them with this. But they have to use a special machine to copy that. It's called write blocker, so that you don't accidentally write to it anything, because computers like to write things when you plug in external devices. So it blocks anything, so you don't tamper the evidence. So it's pretty cool. And then you copy that into the computer using an imaging tool, and then with a write blocker, and then looking at that data. There's different tools. There's one called Cape, another one called PhotoRec, which are pretty good. There's paid ones too. They showed us both paid and free because they wanted free ones so that we can teach them, and if we do a class, UNLV or something for digital forensics, and the paid ones because that's what they actually use in real world. And so, but both of them do the same thing. It's just freeware versus paidware. So we were playing around with USB drives, but they did send us a 1 terabyte hard drive just to show us how long it would take to copy. But it was not viable to run those for all the exercises because it would have taken hours to do each one. But we did get to copy 1 terabyte hard drive just to see how long it would take. And yeah, it takes hours. It's a hard drive, so you're copying an entire drive. So no, we had to mail everything back. All I got to keep was a booklet. That just basically has all the exercises that we did. So yeah, no, it's cool, and especially the triage stuff. So once you get all the stuff, if you're in a rush because you have to present to court, or it's life threat situation, this guy kidnapped someone, you're trying to find where they kidnapped them to or something, they run triage, which is the tool to quickly kind of scan what will be useful, things where the file extension doesn't match what this file signature is, because that means somebody renamed the file extension to hide the file. Those kind of things will pop up. Or they have hashing stuff to match pictures that are illegal. So you see that they match without looking at the picture and whatnot. And yeah, so cool stuff. So we'll see. I might incorporate that into the cybersecurity class that I teach. So, stay tuned, I guess. But cool stuff. Maybe we'll talk about it someday. But yeah, that's what that was about. So fun stuff. I'll like I said, maybe I'll do a quick summary maybe in the semester we have time or something. Obviously we have more important things at hand, such as 302 stuff. It's part of the cybersecurity class I teach is part of the masters for cybersecurity that we have, which is not the boot camp that everybody sees on Instagram advertisements. That's basically a scam. But I think people can take it as an elective, but I don't know if it's going to count towards the CS degree. So unless you have like a elective that you really have nothing to do, then you could take one of the cybersecurity courses. But I wouldn't take the one that I do, because the one that I do is the first one, and it's meant for people that are not tech savvy. So like I teach in basic coding, so it's like a 135/Linux course with a little bit of security in there. But like what I teach for security has to be limited to stuff that people who don't know how to code have to do. So it's not particularly a useful thing for CS students. It's more of like a interdisciplinary for someone who has like a business degree who wants to do it. That's really who it's for. So yeah, I mean, I wish, if you want to do grad stuff, then you do a CS master's or something. Then it's probably a better way around that. So, but yeah, I wouldn't recommend it for CS students, really. It'll be boring and repetitive from undergrad. Okay, let's get this going. Let me start recording. Okay, so now we're recording for YouTube, and so actually, let's just very, very briefly talk about the 3 traversals that you guys learned. So we have the pre-order, we have in-order, and then we have post-order, right? And so just for the most basic of 3s, just do A, B, and C. A pre-order traversal is going to be to visit the left node, to visit the right node. Or sorry. Well, for the pre-order traversal is going to be to print out the current node. What's the syntax that I used in the videos? Let me see for that. I think I used the word P, but I want to triple check. Print, yeah, I use the word P for print. Okay, so I'll use that. So I'm just looking to make sure I'm consistent with the video. So if that's just a tree we have, what we do is we say we print the root node, and then we go left, and then we go right? And then for in order, it's going to be to visit the left first, print, and then right. And then for post order, it's left, right, print. And so in this case, it's going to be for pre-order, we're going to print in the B, then we're going to print the A, and then we're going to print the C. For in order, we are going to print the A, B, C. And in order for a binary search tree, the one that's actually, left things are smaller and right things are bigger, it's always going to print it in the order, like alphabetical order or just numerical increasing order. And then post order is, in this case, it's actually going to be A, C, V. Yeah. So it looks kind of like the in order, but, not quite. So yeah. Okay. So that's like the really, really fast review. Again, this was the first video, so I expected to see that and to kind of know what those are. Those are relatively straightforward. The only thing you get out of practice is doing them faster. And of course, you don't want to make mistakes when you do them, because it's very easy to make mistakes with this stuff. So yeah, so that was just traversals, right? And I guess there's one more traversal. That's the level order traversal, right? And that one would be basically just kind of going on by levels. So in this case, that would simply be B, and then the next level is AC, so you could put BPC. I suppose in theory, it could also be BCA if you're just going in this direction with the levels, but typically you're going to go left to right just to be consistent, okay? So I guess there's that 4th traversal as well. Again, that one's very, very easy to do. At least, interestingly enough, it's easy to do if you have the tree and you're doing it by hand. It's a lot harder to do when you're doing it on a computer, because you have to do what is essentially a breadth first search. And when we talk about breadth first search as the graphing algorithm, then we'll go through a proper algorithm of how to do this. In the meantime, you're just going to have to kind of wing it for the assignment or research it. Okay? So again, those are the traversals for trees. And in this case, it's pretty much binary trees, not ternary, because that would be things would be a little bit different there. And then finally, we have building a tree with a traversal. So when you're trying to build a tree from a traversal, in the videos that you watch, what I'm doing is, first of all, I have to decide how many traversals do I actually need to be able to build a tree. And more accurately would be to say, not just to build a tree, but to build the exact same tree. And by that, I'm saying that every node has to be in the right location in terms of who its parents are and who its childs are. And left and right child, we're sounds weird to say that, but we're discriminating essentially. The left child is always going to be that left child and the right. So like we can't flip those things around. If we flip them, then it's no longer the same tree. And so what we concluded is that one traversal is not enough unless that traversal happens to be actually no, one traversal is not enough, because if we had the level order traversal, that doesn't really tell it to us, because level order traversal could be, let's see, this is A and B. And so both of these trees level order traversals identical, right? But they have the different trees. So the only catch is we could use just a level order traversal, but it has to be of a complete tree. So that means that we have to put in fillers for the stuff that's not there. So like just X's, for example. And now these will be different, because this would be like ABX and this would be AXB. And if this is just all the leading X's, then we don't really need them. You can just get rid of those. But we do have to fill it in. So if we do that, then yes, level order traversal is more than enough. And that's what we do in the assignment. But if you don't have those X's filled in, I'm saying with the empty spots filled in, then level order traversal is not enough to build the exact same tree. The mirror is just a function, but it's not particularly traversal. That's just a thing you do. So that's not as hard as you think, though. When you're doing that, the easiest thing to do is just to traverse a tree and then just flip left and right. So that's actually really easy to do once you finish the assignment. Like it's like a 5 lines of code recursively, maybe even less if you write it like nicely. So don't worry so much about that. But anyways, so level order traversal, not enough to build identical tree. And then pre-order, in-order, and post-order on their own are not enough either. And so what we decided to do is to basically say, okay, well, if we can't do it with one, let's do it with two. And in this case, we have two combinations that we can build. We can build with the pre-order traversal and the in-order traversal. Or we can build with the post-order traversal and the in-order traversal. So as you can see, we always need the in-order traversal and then one of the other two. Okay? Now, there's probably algorithms to build like level order plus another one, like the in-order, but or pre-order, I don't know which of the, maybe level and post. Pre doesn't seem like it would be useful. Either post or in-order. So that's maybe viable. I personally don't know such algorithm, but I'm sure that it could be doable. It'd just be tricky, because all you really need to get from the other traversal is the X's per se, if you don't have them, which is, if you did, then you just use level order. So it's probably doable. So that could be a cool challenge. I don't really want to give it away as an extra credit, because it's not that interesting that you want you to spend time on that, but it will definitely be something cool to see if you could do that. I'm sure you could Google it and find someone trying it out. But anyways, since in the class we only care about these two, because there is one algorithm that works pretty much the same for both. And this is, of course, the second part of the assignment, which is why I split it into two assignments, right? So that you notice they are due back to back, like 1 day difference. That's because it's the same assignment. The only real difference is that I instead of making one big beefy assignment, I split the points into two to make it more points, and also because it's easier to grade that way. So yeah, it's just like adding one more function to your previous assignment. So I think it's 5 and 6 are the combo, or 6 and 7, I can't remember. But yeah, they're basically the same assignment. You just add one more function. Of course, that function is not that easy because it's built into tree function. But yeah, okay. So 6 and 7, thank you. Yeah, so yeah, make sure you keep that in consideration, okay? So I would not, I mean, in theory, you could do that function, that 1 day difference between both of them, but I wouldn't do that. Is it 2 functions? Maybe there's a second function. Oh, well, I guess you're doing from pre and in and maybe post and in. So it might be 2 functions instead, but it's basically the same thing. When we do assignment 7, can we edit main to call it? What do you mean? Well, yeah, I mean, you kind of need to call the function, right, to be able to test it. So yes, that's fine. That's probably another reason why we split it, because how could we show everything together, right? Because it's a menu and whatnot. So yeah, that's fine. Yeah. Okay. So in looking at the video, it appears to me that we did an example of looking. I'm assuming so did you do this massive example that is with a bunch of letters? So you did pre and post. Yeah, pre and post I think you did, right? Or pre and in. You did pre-order and in order. Okay, thank you. Yes. So now we can do post order and end order. So what I'm going to do for that is obviously I don't want to give away the answer. So I'm going to build a tree, very quickly run the traversal of the trees, and then show those, okay? So we're gonna do post. And by the way, is the example you did this one? I'm curious. Like here, you'll see the letters that'll look obvious. Was it this really big example with all those letters? Because if not, definitely check out that series of video, the one that follows, because it'll give you more examples probably. Oh, you didn't do that one? Okay, very cool. So definitely, I don't want to do the same example, obviously, because that, you can watch the video. But if you want to see a massive example, look at all those letters, building the tree out of that massive example. You can watch video 14 of that series of fall 2020 and see me build that on a video. So if after today's example, you're still like, I wish I could see more examples, then check that piece of the video out. And then you'll see more examples. So that might be useful for your review, okay? Obviously though, I want to always do different examples to build more examples, So yeah, okay. So I'm not going to do as big example as that because that's actually massive and took the whole class to do, I think. It's video 14 of the fall 2020 playlist. If you're watching this on YouTube, I will, if I remember to do this, I will leave a link on the description below, but I may not remember that, so we'll see. I will try. I'll try my best. You might have to all send me a reminder like around 8 p.m. tonight. Because I do have back-to-back classes, so by the time I finish Tool 2, I probably will have forgotten. But yes, please, definitely leave me a message on Discord or something, and I'll post a link to that on both Discord and the YouTube description. But yeah, it's literally the next video from the one that you guys watched for the break. While I was taking the course. So, okay. So anyways, what I'm going to do right now is I am going to hide the tablet so that I can build a tree. And then I can do the traversals. Okay? So let me just pick, do you want numbers or letters for this example? Pick what you would like. And then I'll start building it. Numbers. Okay. The numbers, Mason. All right, so I'm going to just build it, okay? And these numbers are not necessarily in binary search method, it's just random, which is good because it makes it harder. The one trick with this is you don't want to have duplicates because otherwise things get really messy. And that was an issue with the assignment, actually. I remember that. Okay, so how many do we have? We have 3, 5, 6. I'm going to go about 10 numbers. I think that'll be good enough. Okay. All right, so we have 3, 6, 8, 10. Okay, so I got 10 numbers in here. I could go bigger. Actually, I'm going to do one more number. Obviously, the reason why I like the bigger examples is because they show all the cases. But then it gets to the point where it gets like too big. Okay, so now that I have my tree, I'm going, obviously you can't see what I'm doing. I'm going to build the 2 traversals that we want to do. So we said we want to do post and then order. So I'm just very quickly going to do that. And then I'll put it in. So let me just not speak out loud as I do it because I'll give it away. Okay. So let's start with the post order traversal. So that's, see, I almost said it out loud. Actually, I mean, I can say the numbers out loud because this is the traversal that we care about. So, but yeah. Not to be very careful, because if I make a mistake here, then this whole thing will not work. And that will be very sad. And by the way, remember what I hopefully, I'm pretty sure I said this in one of the videos, that let me just rewrite the list down here so you can't see it. So remember that in post order traversal, the last number of that list is always going to end up being the root, right? And in pre-order, the first number of the list is also going to be the root. So yeah, okay. So now I'm doing the in order traversal. That one is left, root, and then right. So okay, I'm done now. So what I'm going to do now is I'm just going to bring the 2 traversals down. And then I'm going to hide the tree and make sure I don't scroll up to show the tree. Okay. All right. Here we go. So I was trying to make it nice, but it just became messy. So let me just rewrite it really fast in one line. So that's 15, 10, 21, 88. So I made them, so not get confused, I made them all be double-digit numbers just to avoid us getting confused between them. Obviously, the computer, they don't get confused because they can just become separated. But yeah, okay. So this one is going to be the, I guess, the in order. Yep. And then here's the post order. (42, 44). Oh, and by the way, while I'm writing this, we will have class like normal next week. In fact, I don't expect us to have any other like non-live classes for the rest of the semester, but you never know. But I will not be in my house when we record them, so I will be actually in a different house. So I will be using my laptop. So that'll be interesting to see. I presumed everything will be the same, but we'll see how it goes. All right, so this one's the post. Okay, good enough. So yeah, yep, it will be Mexico stream indeed. So yeah, I mean, I have fiber there, so if anything, it should be better than here. But we'll see. Yeah, I was thinking of recording me going in there just to make it like the introduction to the stream, but we'll see. Okay, so we got them both now. All right. So what we're going to do is we're going to build our tree. And before I even touch it, let me make a bunch of copies of this or at least just let me leave it on the notepad here, copied, because we're going to be writing that a lot of times. In fact, let's just leave one clean version up there in case we lose it. Okay, and so remember what I said, that in post-order traversal, the last value is going to be the root, right? Because again, in order is left root right, or left print right. I like P for print because it's better than R for right. And then for the post, it's left right print. And so as you can see, that's our root because it's the last thing that gets printed. So 21 is going to be our root of the tree. And now where's 21 over here? Oh, did I really do the tree like that? I guess I did. Sus. Now I want to see it. I don't recall. Okay. No, okay. I guess I did that. All right, cool. So yeah, that's fine. Even if we make a mistake, let's just build the tree and see what happens, and then we'll compare. But yeah, so as we can see, this is a very, very heavy tree on balance tree. It's like very, what is it? Right tree, right? Like very right heavy tree. And so that's okay. That's okay. I mean, you could end up a situation where like 21 was at the beginning, and then you know this is literally like root and then everything on one side. So that's okay. All right. And so we already, by doing that, have decided one of the locations of the nodes in the tree, which is the 21. So we can start building the tree. Okay. And so once you've identified what the root of that specific layer you're on, which in this case is the root, then you essentially separate these into two separate lists, which we're going to call the right descendants and the left descendants of that node. I don't say children because this could be grandchildren, great-grandchildren or something, but the point is that they're descendants, okay? So everything to the right of the 21 is going to be something that is going to be a descendant, okay? So something is going to be here. And this is something you would pass in your function. Whoa, shoot it. It started scrolling up there. Okay, I almost spoiled it. All right, and then this is going to be the left descendants, okay? As you can see, there are a lot less of them, which is fine. Again, you don't know what the tree looks like, so you can't really make assumptions that it's a balanced tree. Okay, so now that we have a situation like this, then we can keep going using the same idea that we just pick the next item in the post order. So we're basically working our way this way. In the pre and in order traversal example that you saw on the videos, you're working from left to right. With post order, it's the exact same algorithm, except you don't work from left to right, you work from right to left for the post order, okay? So that means that the next value that we are going to be looking at is going to be the 31, okay? So we know that we have our two lists, and what we just have to identify is where in this is a 31. And as we can see, the 31 is over here, okay? That means that the 31 has to be an actual child of 21. To decide whether it's the left or right child of 21, we see on which list it is. Because it's on the right list of descendants, that means that this is the direct descendant of 21. And everything else in that list is a descendant of 31, okay? So to make sure that we understand that, all of these are children of 21 of some type, you know, grandchildren or something. They're descendants. But only one of them is actually the direct descendant that is like the actual child. And that is going to be the one that's next to 21 here, which is 31. So that means that this is going to get converted. And instead of overwriting it, I'm just going to copy paste it because I like to kind of show you what you would do in a test. Is that, and you're just going to put everything on each side, left or right, based on where they are in relation to 31 in the in order list. So that means that our tree now becomes that. Okay, now it looks more like a tree. So again, what I'm doing is, now that I picked 31, I'm going to go from 31 and everything to the left of 31 is going to go to the left of 31. However, you see that in the in-order list, we have also these numbers, right? You want to make sure you don't actually put those in because those are part of a completely different list. So when we did the 21, we split it into two sides. We split it into this and into this. So when we see the 31, we're only looking at this sub list. We're not looking at the entire list, okay? Think of like quicksort, of how we split the list over and over again. It's the same concept as quicksort. That's why we teach quicksort before we teach this stuff, because it's kind of like the same idea, okay? So you're always going on post order from right to left. And you start out with the first one, which is the root. And then you pick the next number, which is 31. So that's how we pick 31 to answer your question. So essentially, 21, split the list into two based on where 21 is in the in-order list, okay? Do it again then, rinse and repeat. This is recursion. So pick 31, find it, and then split that sublist again, okay? So it's, again, think of quicksort. I mean, hopefully you all get quicksort right now. Otherwise, we're really screwed. But think of quicksort and picking the pivot, right? Imagine you pick your pivot as 21, and this is how you ended up once you did the sorting. You had a left side and a right side, right? And you have your pivot. And then what you do, you feed both lists again into the quicksort algorithm, right? So let's say that we feed this list and we pick 31 as the pivot, and then this is how we end up with after we do the sorting. We have our two sublists, right? But you pass this piece of the list, you don't pass like all the way to the beginning, right? So it's exactly the same system as quicksort when you're dealing with your indices, okay? So obviously, if you're dealing with an actual graph, this is much easier. But you know, when you're building this from a traversal like you are here, you're more than likely going to be using the traversal as a list. So same concept as quicksort. You have a low and a high pointer kind of thing to keep track of where your list begin and end or your sub list. Same idea, okay? So if you get that, reason I'm emphasizing this is because if you get stuck when you're trying to implement this for the assignment, just think back to how you implemented quicksort, and it's the same concept, okay? All right. So anyways, once you split it, now we have two new sort of sublists. We have this one and we have this one. So right now we have, technically speaking, we still have this list we haven't worked with. And then now we have this as a sublist and this is a sublist. All three are going to have to get processed at some point. But we don't decide which to process that way. We just pick the next thing in this post order. So the next number is going to be the 55. So that's the next number we're going to deal with. What does that mean? The same thing it meant with the relation between the 21 and the 31 is that the 55 must be a direct child of whoever that list belongs to. So where is 55 in our list? 55 in our list is right here. Therefore, that means that 55 must be a direct child of 31. Okay? And that means that the other items in that list, which are 16 and 99, which are also descendants of 31, and they're not just any descendant, they are descendants on the right side. That's the right side, yeah. Sorry, I got the mirror thing and it confuses me. So that's the right side. So you know that is the right side of 31, and of those three numbers, we're saying 55 is a direct descendant, and the other two must be descendants of some way or form of 55. So what are they? Are they left or right descendants? Well, 55 happens to be the leftmost item of this sublist, which means that there's nothing technically over here, which means that 55 has actually no left child. It only has right descendants, which are these two. We don't know which one goes first. It could be 16 or 99. It could be either or, but it's both of them have to be there. At this point, we just got to figure out who's the actual child and who's the grandchild. Okay? So again, looking at the sublist, what we did is we found the 55, and then we saw again, like, think of like a quicksort when your pivot is all the way to one side and one of the sublists is empty and the other one has all the numbers, which is the worst case scenario of quicksort. Same concept here. So this right here is kind of empty, and then here we have 2. Okay. So because this is getting kind of cluttered, I'm gonna do one more copy paste of this to kind of update you where we're at. Okay? So now we have this sublist, and technically we have a sublist here which is empty. So that's why we assume that there's no children there. Okay? And we still have the other two. So we still have this one and this one. Okay? Next, we just look at the next number in the post. So that one's going to be 16. Okay, we're 16 up here. And this is why duplicates don't really work with this, because if you're looking through here and there's duplicates, then that can really mess things up. So you really can't have duplicates here. That's the only catch with this algorithm. Oh, here, let me pick another color. It's different. All right, so we look at where 16 is. So this time, instead of doing it with the graph, I'm just going to do it directly here so you can make sure you understand how to do it actually in code. So you look at the 16, and then you look at where that sublist belongs. So that sublist belongs to the sublist of 16 and 55, which are direct descendants of, 16 and 99, which are direct descendants of 55. So that means that 16 must be the direct child of 55. And while we're not there yet, technically speaking, because there's only one sublist now there, there's only one item in that sublist, then 99 is probably going to be the child of 16. But we don't know that, and the code technically doesn't know that, so we just let it run. Okay? So what that entails is that oh, you know what? I shouldn't have modified that so that it could stay the same. Just so that you can see all the steps later. There we go. Okay. So now we got, yeah, they look the same-ish. Let me put one more iteration of that up here. Right there. Okay. So yeah. Okay. So now we went ahead and we picked 16 as we saw. And so again, there is nothing to the left of the 16. So that it means there's no left child. And then whatever's to the right, which in this case is just 1, must be the right child. Okay. Again, it's just one item. So I could just leave it like this and you could do that in the test. That's fine. But in theory, this is actually a list containing one item. So we won't really know that it's actually that's the case in the code until the next piece it runs. It's kind of like quicksort, you know, you could optimize it so you don't actually rerun the algorithm when there's only one item in your partition. But if you do, it's okay. It'll just run and be back with that one item. But you could also add some optimization code to say, well, if there's just one item, then it must be in the right spot, you know? So there's optimizations you can do to the code just like you can in quicksort. But yeah, you'll see that happen right now otherwise. You know, the next thing we pick is the 99. We look at where 99 is. We see the 99 is indeed a direct child of 16. So we pick 99 to be that child. And then you're like, well, what's to the left of 99? Well, to the left of 99, there's nothing. Right? There's nothing right here. And to the right of 99, there's also nothing. So that means 99 has no children. Which is kind of what you can see here, because again, there's just one item, right? So, yeah. Okay, so at that point, you can see that we actually finished, one section of the tree, and now we only have this right here and this right here, right? So you can see that that the tree is starting to take place. We just got to figure out how these go and how these go. Again, we don't pick which one to start working on. We just keep going with the same thing we've done so far, which is just work our way through these. And that's what'll do it for us. Okay, I am beginning to run out of colors. Let's do green. So next thing is going to be 44. So we're going to identify where 44 is here. You can see that 44 is here. So again, we say, okay, where does this 44 belong to? Well, it belongs to the right list of 21, as we can see here, right? Or sorry, no, it's actually going to be the right list of 31. So even though it looks here like it belongs to the 21, it was actually part of the 31. How do you not screw that up? Well, as you're building the tree, the recursion will basically keep track of whose parent is whose, as you can see by this list here. We know that 88, 22, 44, and 42 are all descendants of 31. And yes, they're also descendants of 21, but they're more direct descendants of 31, which is what we care about. So because of that, we pick 44 in the sublist, and then anything to the left of it, let me make a copy of this. So anything to the left of it is going to be a left child of 44, and anything to the right of it is going to be a right child of 44. So that means these will be left child, and this will be right child. So that and that. Okay? Again, how did I find it? Because as you can see, this is the list that I'm looking at. So within this local list, that's what we're going to be splitting. So you can see that gets split here and that gets split here. So like if we pick the 15 or the 20, that's the list we'll be splitting from. But in this case, we pick from this from. So remember what list it belongs to. You don't have to code that because again, the recursion takes care of that for you, but it's good to know. Okay, so this is getting pretty crowded again. So let's make another copy of that. There we go. So now this list is no longer the list we're working on, and all this stuff is done, so we don't really need to keep these here to get confused. We only have 3 lists that we're still doing. We have this one, and this one. Of course, it's just one item. You could optimize, be done with that, but we're not there yet. So we'll do one more. Let's just pick, that. It's like dark gray. 42. All right, 42 is a solo item. Perfect. That's nice. So who does that belong to? It belongs as a child of 44. So you're done. Again, that was the one you could have optimized. But even if you didn't, the algorithm should work fine. So yes. Bam, done. Okay. What color was 99? We never highlighted that here. Let's highlight it. Just make a colorful example. All right. So yeah, that one's pretty straightforward. So we'll just keep going. What does white do? Oh, it's just invisible. Okay. We'll pick light gray then. Light gray, 22. So 22 is part of the sublist. So that means that 88 is going to be a left child of 22. And then nothing is going to be a right child of 22. So that goes there. And like I said, 88 is going to be to the left of it. And it's technically, again, a single item list. So yeah, not much there to say. Okay, so now we're only looking at that one. Okay, just to make sure we're on the same page. So moving on, 88, check 88 there. Again, it's a single item, so we just say, okay, cool. Confirm that's where that goes, and there's no children of 88. And we're getting pretty close to finishing now. At some point we lost the 1 here, so there we go. Okay, so we got 2 numbers left. Like it's no. All right, and brown. Okay, so 10. 10 is the next one. 10 is part of this. That means that 15 is going to be the left child or the left set, which is again just one item, but it's the left descendant. And then here we have right descendants, which is empty. So, oops. Do that. Actually, here, let's copy and paste it one more time. And that's going to be the left. Again, it's technically a single item list, so we're not done yet unless you have optimization. And then for the last number, I think this shade of, yeah, that shade we haven't done yet. Pick 15, 15 there. There's nothing to the left, nothing to the right of that sub list. So it's just a matter of being done like that. And this is the final tree. And now let's take a look and see if that's what I drew. Just put them side by side. Yep, they look identical. So we got it. We did it. So A, my traversals were right, and also B, we built a tree right. So, or we somehow magically got them wrong in both versions, and it worked either way. So yeah. So there you go. We have a beautiful, happy, colorful tree. I think we did almost the exact. How many colors are there technically? Yeah. Well, it's a 4x4, 16. So I guess we have a few other colors, but they're really similar. And one of them is white, which we can't use because it won't show. So. Yeah, but yeah, any questions on that? like stretch. Okay. Cool. Great. So, like I said, that's really the main purpose of today, was to make sure that. I mean, I got a couple of other algorithms I want to walk you through, but that's kind of the important one that you get, because you got to do that for the assignment, and in the test you will do it by hand like I did. So what you want to show your work is kind of like what I did here. So you can build your sub list, and then from there go like that, and then build it again, and just every time you do a considerable step, you redraw it so you can show all the steps. With the single items, you don't need to redraw. I will assume you optimize that. But yeah, so you want to do those as well, okay? Obviously, you don't, this is too complicated for the color stuff for a test, but you can definitely draw the trees like this to show how it's progressing, and the lines as well. So yeah, that's why I recommend for the test. It's no joke when I said paint was the thing that it makes it easier because you can copy and paste, but you can also do it by hand. It's not bad. Just practice so you can do it quickly. All right. So, okay. Moving on, the other trees that I'm going to talk about today are really straightforward and easy. And I believe other than they might show up on the test, I don't think you have to do them in assignments, I believe. But yeah, they're still worthwhile talking about. And the next time, I think we start AVLs, and those are the fun ones. Those are fun. Okay, so the first thing I have here for some reason is BST, which I think I might have talked about, but if not, let's clarify that. I could have sworn that was talked about, but since I have it there, I'll talk about it. So what BST stands for is binary search tree. When is the next test? Probably in like 3 weeks, but I'm not sure. Do the math with the syllabus and figure out. I mean, this is what, like I think we're in week 8 or week 9. So the test is probably in like 2 or 3 weeks. I think I was doing the math the other day, and I think the test might be November 9th or 8th, I think. But I'm not sure. Just go with what the calendar says. And for 302, we can always move the date a little bit. We're not marked that it must be that day. It's not like 202 where like we have a synchronized all classes and like the test will be on this day kind of thing. So I'm not too concerned about that. But it is nice to do it at the same day as them, because then I can just monitor the test times all day. Because otherwise, like I have class right after, so if people are still taking the test, like especially if it has like a DRC thing and they take it longer, I can't answer questions because I'm taking a test. I mean, I'm teaching the class, so I can't answer people. So, yeah. But yeah, do the math and we'll figure it out. Still too long away from that for me to bother, but yeah. Okay, so binary search trees, just to clarify and make sure that we really know what those are, because I thought I talked about them before, but I might have not, is a type of binary tree where you have a parent and you have potentially 0 or 2 children, and any children to the left of the parent has to be smaller. So if we have the number 5 here, or another example, we have the letter C here, then anything to the left of that node, as in like left children, left descendants per se, must be smaller than 5. So it could be in the numbers 1 through 4, or actually, you could actually also put duplicates to the left of it as well. So for example, I could put in a 3. 3 is smaller than 5. Or in the case of the letters, I could put in an A, because that's smaller. If you think about like ascending or descending order, A is smaller than C, right? To the right of the node, so any right children have to be bigger than the node. They cannot be equal. If there is a way that you could put equals ones there, but you have to decide. You can't just put equals on both left and right. You have to decide all equals go to the left or equals go to the right. And either way can actually work, I think. But most of the time you do it to the left. But yeah, don't mix and match. Okay. So, for example, I could put a 10 here. Or in the case of letters, I could go and put pretty much any other letters like X. Okay? Well, that's pretty extreme, but yeah. So, that's what binary search trees are in short. There's no science to that. The definition that I have is basically, I'll just paste it here. given a node n with a value x, if you're searching, inserting a node with value y, you're going to insert the left child if that value is going to be smaller than or equal to x. Otherwise, insert the right child when y is greater than x. So again, given a node n with a value x containing that node, if you're searching or you're inserting something with a value of y, you want to compare the value of y with the value of x. If y is smaller than or equal to x, so again, if you have a number 3 and you're comparing with 5, if 3 is smaller than or equal to 5, put it to the left. If that y is greater than the value of x, put it to the right. So if you're putting in a 10 and 10 is greater than 5, then put it to the right. Okay? So again, that basically says that any numbers that are smaller than 5 or equal to 5 go to the left. Any numbers bigger than 5 go to the right. Okay? And that's because we're looking at this node. But if, let's say, we're trying to insert a 4, where's the 4 going to go? Well, 4 is smaller than 5, so we know it goes to the left. But there's already a node in that location, 3. So what do? We put it as a child of that node. So it could be a left or right child. We do the same comparison. 4 in this case is bigger than 3, so it must go to the right. And that's how you get that. Okay? They said that we wanted to insert another 5 into this tree already here. Well, 5 is less than 5, so you go to the left. But that node already exists, so you see, okay, is 5 greater than 3? Yes, it is. So it has to go to the right. Well, that node already exists. Well, is 5 less than or greater than that? It's greater than that. Okay, and it goes here. Okay, so basically, you keep going until you find a spot where you can throw it in. So that's that search feature of that. So the idea of doing this is because then you're able to access the items the same way. If you say, okay, I'm looking for a 4, you start at the top and you say, well, we know that 4 is smaller than 5, so it would not be found here. It was found in the child on the left side. So you go and check that. So then you look at the 3 and you're like, well, we know that 4 is greater than 3, so it cannot be to the left of that. It has to be to the right. And then you see the 4 and you're like, well, that's what we're looking for. Okay, we're done. The end of the story. Let's say that we're looking for a 6. If we're looking for a 6, we look at the root and we say, oh, okay, well, 6 has to be greater than 5, so it must be on this side. And because this node is not empty, we can keep going. 10 is greater than 6, so it cannot be on this side. That will not work. It has to be on this side. However, there is no children. So because there's no children, we know that if there was a children, then that could actually be our 6 that we're looking for. But because there isn't a child, then it means that this tree has no 6 in it. Because that's the only spot in this current tree where 6 could actually be. It's impossible for it to be anywhere else but this spot right here. Because otherwise this 10 wouldn't be here. And there will be children to this stuff. And so, again, that's how you confirm that that is not found. Okay? So, what else do I want to say about that? In terms of code, I do have some code for the previous lecture. Yeah, I'll throw that in. Oh, and by the way, I did show code on the video, the recorded video, that I do like to ask in the test. It's the one case where I like to ask code in the test because it's a lot easier to explain than actually explaining it with text. And that's your insertions, your traversals, because it's just 2 lines of code. But here's how you would insert something into a binary search tree, which is, again, the same thing that you just coded here. So it's a recursive insert, and you pass in the root. And then when you pass in the root, you basically check if the root is empty, which means the tree is empty. If it is, then you just dump it at the root and you're done, good to go, move on. If it's not empty, then you keep going. And in this case, you are going to go ahead and I lost the thing here. There we go. Okay, so if it's not empty, then again, you just check whether the contents of your node that you're trying to insert are smaller than the contents of the root. And if they are, then you are going to go ahead and, well, technically here, yeah, if root D is smaller than ND is going to be the root node. The root and then the n is the one you're inserting. Yeah, okay. So if the value that you're inserting is smaller than or equal to the root, see, this is backwards than what I wrote it, so it kind of threw me off because I wrote it backwards. But yeah, this is basically saying if the root is smaller than what you're trying to insert, which means that what you're trying to insert is bigger than the root, then, but that will go to the right. So maybe I have this flipped. Do I have this flipped? Let's see. Say the root has 55 in it. 55 is less than 20 or equal to. So that means that this cannot be, so that would mean that this is like 80. So if 55 is less than 80, then go to the left. Yeah, this is flipped. Maybe I was doing something different here, but this is flipped. This should be greater than. I don't know why I have it like that. But yeah, okay. Yeah, because I mean, if the root is bigger than what we're trying to insert, then what we're trying to insert is smaller, right? So it would go to the left of it. So you throw it to the left, yeah. Otherwise, insert it to the right. So that should be flipped too. I don't know what was up with this. And I guess I use L for right and R for root. So, okay, that'll look like that. But yeah, that's fine. That means right. In fact, we'll call that RI, and less we'll call it LE, just to not get confusing. Or I guess I called it lowercase r. Ah, no, I see what I'm doing here. Okay, this is why I don't like just pasting code, because then I don't remember the code and I have to like understand what this code's doing. What that code is doing here, this piece of code in here, is just checking whether it's null, and if it's empty, then just put it there. Otherwise, call the function to insert to the child of the child. So that's okay like that. And then otherwise, then that's okay too. Okay, there we go. Now it's nice. So the only problem this had was for some reason this was flipped around. Okay, so now this code is valid. So let's look at it again from the top. So we're having our insert function and we have two parameters. This one's the one we're inserting, and this is the root. And so we're checking first if the root is null. So this is like an empty tree. Well, technically this would be a subtree as well, but yeah, it's an empty tree there. And if it is, then we're just going to just throw in our node and basically call it a day. So to optimize this code, I can turn this into a else if like that. Okay? All right, that's one case. The second case is that it's not empty. So now we're going to check whether the item that we're trying to insert is smaller than the root. Okay? So smaller than root. Or also smaller than or equal to, actually. Yeah. Okay, if it's smaller than or equal to the root, that means that it has to go to the left. So next we're going to check if there is already a child there. If there is a child there, then we're just going to call the insert function and pass in that child as the new root, which is what is happening here. And then this is the child, the node that we're wanting to insert. So otherwise, if there is no child, then we can just go ahead and insert it by just assigning it right there as a child. Okay? Otherwise, up here, this else is for a right child. In this case, with the right child, what we're going to do is if there is no right child present, then just go ahead and throw it in and we call it a day. Or if there's already a child present, which is what this else does, so already a child there, then we are just going to call the same function again, recursively. And instead of passing the root node, we're passing the child node that exists. So we're good to go. Okay? So that's just, there's a lot of ways that you could write this. You could also do the insertion at the top of this, but yeah, it's good. Okay? So anyways, it's very trivial code, but it's still nice to show. So I have an example of inserting items. I guess we can do one example as well. So here, let's just put a bunch of numbers, 4, 5, 1, 3, 2. And let's just build a tree out of this. In fact, here we could have duplicate. So here, let's just do that much, okay? If we're building a binary search tree, then we just go from left to right. So we start with that. So we're gonna go ahead and say 4 goes there. And then 5 has to go in the binary search manner. So it has to be here because it's bigger than 4. The 1 is smaller than the 4, so it's gonna go here. When we look at the 3 is bigger than the 4. Sorry, it's smaller than the 4, so it goes to the left, but 1 is already there. So then we are going to put it to the right of that. And if we're looking at the code, for example, let's do it with 2. So if we're looking at 2, then the first thing we do is we compare it, we see if the tree is empty. It's not, right? So we move on from the if to the else if. And then we say, okay, let's see what the current value of that root is. Well, the value of the root is 4. So is 4 greater than 2? Yes, it is. So then we go into this line of code right here. Is there already something there? Yes, the 1 is there. Okay, so we just call the insert with that passed in as the root. So we're passing it with the 1 passed as the root. So we start the function again. Is this value empty? No, it's not. Okay, fine. So then we go ahead and say, all right, is the value of this item greater than the value of what we're trying to insert? And it is not, because 1 is definitely not greater than 2. So then we go to this else clause. Okay, is that value current and empty? No, it's not, because there's something there. All right, so then just go ahead and call it with that number. So we're calling it now with the 3. Okay, so we go to the top of the code. Is this empty? No, it's not. This might seem redundant, but it's important to have this piece of code for the first node, for when the tree is empty. So, okay, so is the value in the root greater than what we're trying to insert? Yes, it is, because 3 is greater than 2. Okay, so we go in here. Is that child empty? Yes, it is actually. There is no child to 3. Okay, then just go ahead and insert it to the left of that. So that was the code equivalent of doing that. As you can see, it's a lot of recursive calls just to get there. Because now we just return from that, return, go all the way to the top, and then say we're done. So, yeah. Recursion is not the most efficient thing, but this is like 10 times easier than trying to do this iteratively. So yeah, like a flowchart. Recursion typically tends to work like that actually. So it's not like this is a special case. This is indeed always like a flowchart style. But yeah, I'm not going to do the rest of them with recursion because that would take too long. But yeah, that's how you run it. You know, especially if you're trying to debug. You know, make sure that that's what you're getting back. Print out the values and whatnot. But this code now should be robust after we checked it. So yeah. Okay. All right. So let's put in the 3 then. So again, let's start with the root. 3 smaller than that, bigger than that. So here we have 3 and 3, right? So they're equal. So we said equal go to the left. So we actually throw it here. But there's already something here. 3 is greater than 2. So it's actually going to go like that. So this looks weird, but it works. So yeah, I guess just kind of accept that. And then with the 2, it's the same thing. It's actually going to end up all the way here because it's going to go like smaller, bigger, smaller, same. So left side and then 2. And finally, that 1 is actually going to go here. Okay, so it looks weird. Looks very inefficient because as you can see, again, this is like a very heavy tree to this side, but that's not something we worry about until we get to AVL trees next class. So yeah, okay. So yeah, it's good to do some examples of that. So as for the other kinds of trees that I have listed here, so I have lowest common ancestor and expression trees. Let's just do an example of expression tree first. These have Geeks for Geeks links that I'll link you here. Let me Google. Geeks for Geeks, expression trees. Here you go. And then the other one's LCA tree. They're relatively trivial. Like I said, you don't really do them in assignments, but they're good to know because they might show up in the test. I really don't remember if I put them on the test or not, but they might be, so play it safe. So expression trees are cool because you can actually represent mathematical operations with these. And then if you want to just do a traversal, then you can actually get like the in order traversal, like postfix, prefix notation, infix notation. You can get these kind of things by just doing the traversals. So they're pretty cool. So I'll just give you a very basic example of them. So if we have something like this, 3 plus 2, you know, if you're, this is basically you basically want to make the parent node the operator and the children the operands, unless you have multiple operations happening together. So for example, if we have, you know, like 8 times 3, but instead of doing 8 times 3, you might want to make this multiplication be the result of an addition. So like 1 and 2, which is 3 of us still. Okay, so this tree says, okay, before you can do this multiplication, you have to resolve what the addition is. So you can do the addition there. Okay, so it's a good way to represent operations and like not worry about order of operations because it's built into this. And if you do the traversal of this, like let's say we do the let's do the in order traversal, we see that we get 8, and then we get the times, and then we get the 1, and then we get the plus, and we get the 2, right? So that's the in order traversal, but we would technically need parentheses for that to actually work out mathematically. However, if we do the pre-order traversal of this, then we get a times, then we get an 8, then we get a plus, then we get a 1, and then we get a 2. That's pre-order. And if we do the post-order, then this becomes, so we go 8, and then we go 1, 2, plus, and times. So this is actually also prefix notation, and I believe this will be postfix notation, because with postfix notation, you push all these to a stack. So you get 8, 1, and 2, and then you pop whenever you see an operator. So you pop the 1 and 2, and then with the plus, add them together, which you get the 3. And then you push that into the stack again. So now your stack has an 8 and a 3. You pop them both to do the multiplication, and you do get 24 with that one. I'm not very familiar with prefix notation, but I think you kind of do something similar. But I don't know. Postfix is what I've heard. But yeah, so those are cool. Just kind of a nice thing to represent. If you don't know what prefix notation is, if you know what postfix notation is, that's I think it's called Polish notation, and you can just kind of check it out. Like really old school hardcore engineers would do postfix notation. Reverse Polish notation, that's what it's called. They would do that because you don't need parentheses for that. So like, you can see that like, whereas in infix we need the parentheses, we don't need parentheses for this for it to work. So I guess it's less writing, but like not, you know, it's, I don't know, I don't like it. It's not visually easy to understand, especially when you get something really complicated, not like something trivial. But you know, it's there for you if you want to use it. So that's expression trees. It's another nice example of trees that we have. And then lowest common ancestor is just an algorithm to find. So whenever you're trying to find the lowest common ancestor of a tree, it's just saying, okay, if I give you 2 items of this tree, try to find out who their nearest ancestor is. So like, imagine I say, who is the nearest ancestor between you and your cousin? Well, okay, who's your dad? Or who's your mom? And then like for your cousin, who are their parents? And like, you know, one of those 2 is probably, well, I mean, if you're not adopted or something, but if you're like, if you're like genetically born child, I guess, what do you call that? Biologically born, you know, let's just say that like your cousin's mom is your dad's sister. Okay. So if that's the case, then, you know, the parent of your dad is also the parent of your dad's sister. So that would be the common ancestor, right? So that would be your grandparents, right? Or their parents of the both. So that's kind of what the algorithm is doing. It's just an algorithm to find that. So for example, let me give you some values. So let's just say we have the following tree. I'm doing letters because on Geeks for Geeks they have numbers. So I just want to give you something different. Let's use a different one. So for example, if I say, what's the lowest common ancestor between T and C? Well, that's just going to be whatever the closest link is. So that's X, okay? However, if I say what the lowest common ancestor is between C and D, that's just a parent. It's like, what's the lowest common ancestor between you and your sister? Just your parents. If we make this a little more interesting, so maybe like W and then G. So the common ancestor between those is going to be B. However, if you say what's the common ancestor between D and W, so like that, well, that's just going to be B. Now here's the trick one. What if I say what's the lowest common ancestor between B and C? Will just be itself, right? What's the lowest common ancestor between you and your parents? Well, just your parents. Okay, so that's not like a trick that like you have to go one layer up or something. And the way you do this in code is relatively easy. You just start with the root node, and again you go with recursion, and then go all the way to find the two nodes that you want, and then once you find them, you return from that recursion, and then you try finding the next one. So for example, let's just say you're trying to find the lowest common ancestor between W and D, okay? So it's kind of like you do your traversals. You try to find, first of all, where W is, right? So, you go through here, you go all the way here, and then you find W. When you find W, you try to find using any traversal really, but you can use Inorder Traversal. You try to find where C is. So obviously there's no children here, so you have to go back up to C, and then you try to see where that is, and you can't find it. So you go back up and you see that and that. Here, let me do the Inorder Traversal because this will make more sense. So if you do the Inorder Traversal of this, you end up with T, A, X, W, C, B, D, and G. Okay? So as you're doing the traversal, you find W, right? So then you just keep going until you find where D is. Okay? So, you see C, you see B, and then you see D. Because you see D right here, it means that this is the one of these, because this is the Inorder Traversal, one of these has to be the ancestor for that. And so the way you figure that out is you basically check the parent of who the parent of this is, and then just remember who the parents of these were. So this was the parent of that, and then that B was the parent of C. So then you kind of do this is the case, okay? It's a lot easier to do. You can see, again, we're not going to code this as an assignment, so if you do this, you would only do this by hand. But you can look at the example in the in Geeks for Geeks if you want to see what the code would look like. But it's not particularly hard to do this. There's a lot of ways to do this as well. So yeah. Just wanted to share those really fast, just because there are more examples of trees. But the real examples that we care about are going to just be binary search trees. That's the ones we are interested in, because, just to kind of lead you up on that for the last 2 minutes, these binary search trees that we did are cool because they allow us to access things quickly, as long as the tree, if you think back to your properties that we talked about like 2 weeks ago, we said that like the height is going to be the log n, and then you do the ceiling function of that, n being the number of nodes in the tree. And if we can keep that height at a minimum based on that math formula, then the access time to any of these nodes is logarithmic, and logarithmic search time is really good. That's like binary search, but the difference is here we can just throw in any nodes when we want, versus like an array having to move things around. So the question becomes, can we keep the log n access time while also making the insertion time be as quick? And we can do the insertion the same way as access, so that's okay. And deletion, easy. It's like a linked list. You can just throw the nodes away, right? The only tricky part is when we insert nodes, the height can get messed up, like here. So can we make the insertion in a way that's not going to mess up the height and make it more what we call a degenerate tree? I'll talk more about that term next time. And the answer is yes, we can, with an algorithm called the ABL tree. And that is what we'll cover next time. Okay? But for now, that's more than enough. Again, Be sure to check out more examples of building trees if you're still stuck on how to do them from the videos. Also, you can probably find stuff online. And that's it. So, any questions before we end the class? It's a lot of material for today. For that expression tree, are we doing that for an assignment or is it going to be on the test maybe? It will not be on assignment because I don't remember. As for the test, it's possible you could have one, but if you do, it's just going to be like, here's a math operation. Build a tree for that. So like I would give you something like, again, I don't remember if I have it because like, as you can see, some of these algorithms take a lot of time. Like building a tree from a traversal, which you will definitely have on a test because that's important, takes a while. And so do AVLs. So like, we don't really have enough time to ask you some of these. But, you know, I might, you know, depends. So, you know, you should still know it. It's easy enough that you can, you don't really need to study this. But like, yeah, I could give you this and be like, build a tree for that. And it's not going to be harder than that. I'm not going to do like a 20-term mathematical operation to compute like the area or the volume of like a galaxy or something. I don't know. So, yeah. It's still good to know though, just in case you ever run into them somewhere. Or like an interview they ask you or something. Remember, all this stuff is like interview material a lot of the times. Especially when we get to the graphs. But trees are also in there. But even basic things like write a program to give you the, I saw this on Reddit, write a program to give you the two biggest numbers of a list. That's pretty trivial, right? Or I hope you think it's trivial. Of course, the joke there was, they said, well, I just got to sort the algorithm and pick the last two numbers. And you're like, come on, that's going to take you, even with the best sorting algorithm, n log n time. You could do this in n time, right? So, yeah. I hope that they would ask you for more than just fist buzz. But they probably will ask you that too, just as the first question to make sure you're actually code proficient. Basic code proficiency. But all right then, I have to get ready for the next class. So thank you all for watching, and I will try my best not to forget to post the link to the other video. All right. So until next time. Oh snap! I forgot to hit record. I actually hit the virtual camera. So for today's video, I will have to extract the video from the Twitch. So it might take me longer to upload to YouTube, but yeah, yep, I've done that. This has happened before, but yes, I will do that. So it might take a little longer to see the video, but I will post it, all right, on YouTube. For now, just Twitch if you want to see a replay. All right, see you all later. Thanks for watching.